Good morning, students. Today we are going to discuss a new chapter, that is electromagnetic induction. In the last chapters we have studied that when a current passes through a conductor, magnetic field is generated in it. And if there is a variation in the current, there will be a variation in the magnetic field. So a reverse process is also possible. What I mean is, whenever there is a change in the magnetic field, a current can be induced. That is what we call it as electromagnetic induction. So before going into detail about the electromagnetic induction, let us first discuss what is magnetic flux. Magnetic flux through any surface is the number of magnetic lines of force passing normally through a surface. It is the total number of magnetic lines of force passing normally through any surface. So we can write magnetic flux as phi. So here in this figure you can see I marked a small surface area ds and B is the magnetic field. I draw a normal which is written as n cap. Normal means it is a vector which is passing perpendicular to any surface. So I draw the normal. The resolved component of B along the normal is marked as B cos theta. Now look at the equation. Flux due to a small surface is d phi is equal to integral B dot integral ds, which can be written as B ds cos theta. So flux passing through any small surface is given by d phi equal to B ds cos theta. So how will we get the total flux? The total flux can be obtained by integrating the second equation. Therefore we will get the answer as phi is equal to vector B dot vector A, or I can say phi is equal to BA cos theta. Flux is a scalar quantity, and we can say positive flux and negative flux depending upon the direction of the magnetic field and the area vector. If magnetic field and area vector are in the same direction, then we will say flux as positive. And if magnetic field and area vector are in the opposite direction, we will say flux as negative. More precisely, we can speak like this. If the angle between the magnetic field and the area vector is acute, then we can say flux is positive. And if the angle between magnetic field and area vector is obtuse, then we can say flux is negative. And what else if the angle is 90 degree? Then we can say flux is 0. Okay. So we have got the equation phi is equal to BA cos theta. Based on this equation, what are the factors in which flux depends? Flux basically depends on three factors. The first one is strength of the magnetic field. So when magnetic field is increased, the flux will also increase. And number one, area of cross section of the coil. If area increases, flux will increase. And the orientation of the coil with the magnetic field. So you can think like this: phi directly proportional to B, directly proportional to A, and directly proportional to cos theta. Okay. Magnetic flux, as I told earlier, magnetic flux is a scalar quantity and SI unit of flux is Weber, or we can write Tesla meter square. And CGS unit of magnetic flux is Maxwell. 1 Maxwell is 10 raised to minus 8 Weber. Magnetic flux per unit area, that means phi by A, is called magnetic flux density or strength of magnetic field or magnetic induction. Remember these three names: magnetic flux density, strength of the magnetic field, magnetic induction. All these three represent the same thing, which is capital B, our magnetic field itself. These are the different names. Now let us move on to Faraday's experiment. Electromagnetic induction, the phenomenon was first discovered by Michael Faraday. For that, he did 3 experiments. I will just briefly say what are the 3 experiments he did. You have already studied this in class 10. It is just a revision for you. So what Michael Faraday did is, he took a solenoid, connected the solenoid to a galvanometer, and he moved the magnet towards the solenoid. As he moved the magnet towards the solenoid, the magnetic flux linked with the solenoid increases and current is induced in the solenoid. And when he kept this magnet stationary inside the coil, at that time galvanometer does not show any deflection, because at that time there is no change in the magnetic flux. Again, when he moved this magnet away from the coil, there is a decrease in the magnetic flux and current is induced in the coil again, but it will be in the opposite direction. Now you can look at the direction of the current which is formed in the coil. When we look from the side where the magnet is introduced, you can see that as the north pole of the magnet is introduced into the coil, the current in the coil is flowing in the anti-clockwise direction. Similarly, if I introduce the south pole into the coil, current will be in the clockwise direction. So remember these directions. If the north pole is entered into the coil, the current will be in the anti-clockwise direction, and if south pole is entered into the coil, the current will be in the clockwise direction. Now what else if we withdraw the bar magnet from the coil? The current will reverse. That means if the north is withdrawn, then the current will be clockwise. If south is withdrawn, then the current will be anti-clockwise. So from this experiment, we understood a movement. Due to the movement, there is a change in the magnetic flux and current will be formed. Now let us see the second experiment. Instead of using a bar magnet, what he did is, he connected another solenoid to a battery. We studied in class 10 that when current passes through a solenoid, the solenoid behaves like a bar magnet. So instead of the bar magnet, he took another solenoid and connected to a battery. This solenoid behaves as a bar magnet. He repeated the same pattern of the experiment and he got exactly the same result. Now let us see what is his third experiment. In first 2 experiments, a motion is required. In the first experiment, we moved the bar magnet. In the second experiment, we moved the solenoid carrying current. Here, what he did is, he didn't move anything. Instead, he just kept a tapping key in the second solenoid which is connected to the battery. And instead of moving the solenoid, he just pressed the tapping key. When the tapping key is pressed, the circuit is on the current in the solenoid C2 will increase. So magnetic flux will increase and an induced current is formed in C1. Now, when the tapping key is released, then the circuit C2 is open. So the current in the coil C2 will decrease, the magnetic flux also will decrease, and as a result, induced current will form in C1 in the opposite direction. So in the third experiment, what Michael Faraday did is, he did not move anything. Instead, he found another way to increase and decrease the current, thereby increasing and decreasing the magnetic flux. And he got exactly the same result as he got before. So based on these three experiments, he understood one thing. Motion, relative motion is not necessary for producing induced EMF. The only thing which is required is there should be a change in the magnetic flux. There should be a change in the magnetic flux. It can be done either by increasing the current, or by increasing or decreasing the distance, or by changing the orientation. Okay, either you can increase or decrease the current, that is number one, or you can increase or decrease the distance, number two. You can change the orientation between the two coils, that means the angle theta. So based on these three techniques, actually what we are doing, we are just changing the magnetic flux. So Michael Faraday brought the two laws of electromagnetic induction. The first law of electromagnetic induction is, whenever there is a change in the magnetic flux linked with the circuit, an EMF and hence a current is induced in the circuit. Whenever there is a change in the magnetic flux, an EMF is induced in the circuit and a current is also induced in the circuit. The current will last only so long as the magnetic flux is changing. That is the first law. Now second law, the magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. That means how much faster the flux changes, that much more current will be induced, that much more EMF will be induced. That is why it is said the induced EMF is directly proportional to rate of change of magnetic flux. So we can write the equation like this: E proportional to d phi by dt, E is equal to K into d phi by dt, where K is a constant. And the units are chosen such that the value of K is 1. So finally we can write E is equal to d phi by dt. E is the induced EMF. Induced EMF E is equal to d phi by dt. And it can be written as phi2 minus phi1 divided by P. Michael Faraday does not say the direction of the induced current, and the direction was set by another scientist named Lenz, and according to Lenz's rule, the direction of the induced EMF or induced current is such that it opposes the change that produces it. The direction of the induced EMF is such that it opposes the change that produces it. So our equation now becomes E is equal to minus d phi by dt. We will discuss more on Lenz's law in the next section. Thank you.